Hey everybody, welcome to Bill Sky, the Assembly Guy, and what this video is going to be about logical operators for the ARM microprocessor or CPU. Now this one's what came after the x86-64 Intel description, and the reason is because ARM is really a different type of architecture. ARM is what they call an RISC, Reduced Instruction Set Computing Processor. It doesn't have as many instructions as the x86-64, which is a CISC, Complex Instruction Set Computing Processor. So it takes more code in an ARM program to do the same thing that you can do in a x86-64 CISC processor. However, the instructions in ARM are much more synced up. They only take one clock cycle, in general, and they're just much easier to create a much more efficient program. So I believe there's something like 123, maybe 210, I can't remember the exact number, of instructions in an ARM processor, where in a CISC x86-64 processor there's over 1,000. So big difference. So let's do logical operators right now, and we're going to do it in Linux. Let's get going. So I'm going to go ahead and start up a 32-bit ARM template here, and let me make sure that's the right one. Yep. So I'm just going to click on that and say extract here. I'm going to call this ARM 32-bit logical operations. And let's take a look at our code. So my template has some code here for printing hello world. You can comment that out if you want. We might do that. But the first thing we want to do is we want to create some data that we can do ands, nots, ors, exclusive ors with. And let's do that up here. So I'm going to create a pretty large number. Actually, it's not a large number. I'm going to create a word, a 4-byte number, and we're going to do this all in binary to make it very, very easy to understand what's going on. So I'm going to say dword binary 1, and I'm going to say that that's a word, and I'm going to give it 001, 0001, 0111, 01, 01, 01, 0111, 01, 0111, 0010. And this is binary because I put 0B in front. So let's make sure I've got 32 bits here. Oh, I lost count. Yep, exactly 32 bits. All right, so the rest of them are going to be much easier because we're going to use that as our legend. Let's create another one. And this one is going to be a word also. What we're going to do is we're just going to turn on or have the last 4 bits as ones. Let's create a couple other ones, and these are going to be used as masks, or, well, they are bit masks, right? And we're going to make the 14th one. We're going to make this one here a 1. And then I'm going to copy this, and you'll see why we're doing these specific values here. I give it a name and I'll put a 1 in there. Okay, so we've got our data. These are all binary, and you can see right here, if you took the logical operation, if you watch that video on logical operations, the theory behind them and how the circuitry of the CPU works, I think you pretty much can see why we're doing it this way, because we're going to do ands and ors and stuff like that. Okay, so the first thing I want to do is I just want to test an and. And what I like to do, excuse the pun, what I like to do is I like to copy these things down here near my code so I don't have to keep jumping up. And I do that just so I can take a look at what I'm doing as I'm learning. So what I'm going to do is, with ARM, it's a lot different. So I have to load the address of our variable. And in fact, I'm going to use R0 as my address register. So I'm going to load into R0 the address of my dword binary 1. So that's going to put the address of dword binary 1 into R0. Now I can't tell you how important it is to do comments in this kind of coding because it's going to keep your mind straight. All right, so now let's move the value found at that address into R1. So put the dword binary value into R1. All right, let's load. So what we're going to do is we're going to load into R0 this big thing, and then we're going to load into R2 this one, and then we're going to AND them. So I can actually just copy and paste this, and we're going to use R0 as our address register for this. And then we're going to go ahead, and I'm changing the comments. Please, please, please take my word for it. If you don't comment your code, good luck. Okay, so what we have is we have this number right here in R0. I'm sorry, R1. And we have this number right here into R2. Now let's go ahead and AND them. So I'm going to say AND R1 with R2 and place that result into R1. Now I'm going to replace it into R0. So we're going to AND R1 and R2 and place the value into R0, the result of that AND. So we're doing this one and this one. When you AND those together, all of these zeros are basically going to zero out all of these, not within the register, but as a result of the AND. And then every place you see a 1 here and a corresponding 1 up here, it'll stay its 1. So the only one we've got is this one right here. So the value of R0 at the end of this should be a 2, because this bit which is on and this bit which is on, it'll keep them on, so that is a binary 2. Let's go ahead and build that. And I think I've got some variable names wrong here. Oh, it's because these are, I can't define variables inside the text section, so I'm going to make those into comments. Okay, so let's go ahead and debug this. And this works because I'm using my templates. So what we're going to do is we're going to be watching. I'm just going to step through all this. And we're going to be watching R0. We want to watch the R0. And what we did was we analyzed what should happen because of our knowledge of the AND operation. Let's see if that's really what happens. Yep, it's 2. So the only bit that is still on from that operation is this bit right here, because that bit ANDed with that bit. A little bit hard with the mouse. With that bit means it's a 1. Everything else is going to be 0 because there's no associated 1 1 1 1 1 1. It's 0 1 or 1 0 or 1 0, right? So that's why we have the number 2 there. All right, so that's AND. Now I'm going to put a comment here. And I'm going to just copy this, because now we're going to take a look at the OR operation. And just so I can keep these right there. And again, you don't have to do this, but I do this to keep track of my data so I can see what's going to happen. All right, so what we're going to do now is we're going to do the OR operation, and we're going to compare the same 2 exact ones. So we're going to do the OR operation, and instead of AND, we're going to say OR. Say OR. All right, cool. So that was really easy to switch over to OR. Now it's not OR as it is in x86-64. It's ORR. Okay, like a little bit of a stutter. And let's see if that built. Okay, so that built just fine. Now what are we going to be ORing? We're going to be ORing this with this, And what we should get is that we should get this number with this bit turned on and this bit turned on. Those two bits turned on. So it's going to be like this, but with those other. So what would that look like? Let's go ahead and draw it out. That number should look like 1, like that right there. Because this bit is a 0, this bit is a 1, we OR those together and we get a 1. This bit is a 1, this bit is a 1, they're both 1, so that's going to stay 1. That bit is a 0, that bit is a 1, ORed, that's going to be turned on. And same here, that bit is a 0, that bit is a 1, and since we're ORing those two 4 bytes together, that's going to be a 1. So that should be our value. Now, if you want to figure out what that is without having to do all the math, there's a great calculator out there for doing binary stuff, and it's called Speed Crunch. I'm amazed I don't have it. So let me go ahead and show you that. So I'm going to go ahead and install it on Linux. Speed Crunch is also available on Windows and Mac, I believe. And there it is. So what I'm going to do is I'm going to take this number right here. Actually, let's take this number. This is the one that I have ORed manually. I'm just going to copy it. And let's see what the decimal value is. And we need the 0B in front. So the decimal value is 58,09279. Pretty big number. So I'm going to put that over here on the side. And the reason I did that was so I could verify that what I'm saying is going to happen is actually happening. All right, so let's save and build this. We're just validating that we know what we're doing here. Okay, so let's go past the AND. And we're looking for the ORR. There it is. And let's see if we get that. 58,09279. 58,09279. So that's what happened. So I'm going to quit. So that's ORing those two values together. We get that. Now you could put this, you know, below it so you could just kind of see the result. And you could just, you know, OR each bit one at a time. So that's OR. Now let's do exclusive OR. So I'm going to cut that out. I'm going to put it down here. Again, this is just for learning how these things work. And then I'm going to copy my code for OR and put it down here for XOR. And okay, test the XOR. We're going to do the exact same data, except instead of OR, we're going to say EOR. EOR stands for exclusive OR. And what should that result be? The EOR result. Well, let's take a look. So what we're going to do is everywhere we see two zeros, like here and here, that's going to be a 0. So we have one there. This is a 1 or a 0, so that's going to give us a 1. These look like zeros. That's going to be a 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1. And then we're going to have a 1, 1. Now 1 XOR 1 is a 0. And then a 1. So that's what it should be. That's what the value should be. So I'm going to go ahead and copy and paste this into my Speed Crunch. And it says it's 58, 58. It's kind of difficult to read with that font, but it looks like 58, 58, 09277. So let's see if that's what we get. when we debug this. And now we're looking for the EORR, or EOR, sorry. There's ORR. All right, here we go. Oh, did I not make it? I must not have built it. There we go. Yes, I hadn't built it. So that's why the code wasn't there. All right. So we're looking for the EOR. There's the ORR. Okay, there's the EOR. Now we're going to be looking up here in R0, and that's 5858092777. There we go. 5858092777 in our calculator. So pretty cool. So that's exclusive OR. Now let's do NOT, and remember NOT is simply a flip of the bits. Now in x86-64 we actually have a statement called NOT. In ARM we really don't have that, and I'll show you what we do have. So let me copy this information because I don't want to have to type all this code again. And what we're going to do is we're just going to NOT this guy right here. So we're going to load it into R1, and then what we're going to do is we're going to say MVN R1 R1, and this is going to NOT the contents of R1. Now R1 is going to be this right here. So what's the result of the NOT going to be? The NOT result. So everywhere you see a 0, you're going to put a 1. A 0 where you see a 1. And that should be our number. Now let's grab that, copy it. Let's put it in a speed crunch. See what we get. And that number is difficult to read again. Let's see if I can highlight it. That number is 3709158029. Now, the most significant bit is going to be turned on, so the debugger, GDB, might actually show it as a negative number. What would the hexadecimal number be on this? So the hexadecimal number would be, this is 8, 4, 12. This would be 8, 4, so that's 12, 13, so that would be a D, I believe. Yes, so that'd be a D. That as well would be a D. That would be a 2. That would be an A. Hope we're doing this right. That'll be a 1. This would be a 4. And what I'm doing is I'm just finding every 4 bits. And this right here, I believe, would be a D. So I believe that would be our hexadecimal value. And let's see if that's right. Okay, so it made okay. Let's go ahead and debug this. And we're going to be looking for the MVN statement in the debugger. So we're going to go ahead and just step through every one. Okay, so let's see what we've got. And as I thought, the debugger is showing a negative number here, but let's see if we got our hex right. DD, oh, looks like we've got, we have some errors in our calculation. Yep, that shouldn't be a 2, that should be a 1, so I did that wrong. That should be a 5. That should be a 0. This should be an 8. That should be an A. And I believe that's a D. So let's see if our number's right. DD154. Looks like we still got something wrong here. So I'm anal about this. Let's fix this. So that's a D, good. That's a D, good. That's a 1, good. That's a 5, good. That's a 4. That's a 2. That's an 8. And that's a D. All right, I think I got it this time. Yep. So our number is the same. Again, I wish the debugger would show it to you in binary. You actually can in GDB, but oh my goodness, the syntax is just horrible. So maybe I'll do a GDB debugging video as well. So that's our not. Whew. So that's all we've been doing today, is just doing those knots. Now, like I did in x64 or x86-64, I want to use this to find out. I want to use some of these to find out if a bit is on. So what I'm going to do is I'm going to copy these down here, and now let's use these as a bit mask. So this one right here, this will be our first bit mask. I want to see if the 14th bit is turned on. This is how you can do this. So I'm just going to say, is the 14th bit turned on? And the way we're going to do that is in R0, I'm going to do the same thing. I'm going to load in R1 our first number. Now it'd be nice if ARM lets you do this all in one statement, but it really doesn't. You have to load the address into your register and then dereference that register to put the address in. So then I'm going to put into R0 the address of our mask, and that was dword binary 3. Then I'm going to load into R0, why not? I'm going to load our mask into R0 from R0. So this is our number to test. This is our, our number to test, and this is our bit mask with bit 14 turned on. And that's what a bit mask is. You turn on the bits that you're searching for. Okay? So then what I'm going to do is I'm going to do an AND S. Now what an AND S does is that it ANDs this with this. It'll put the result where we tell it to put it, but it will also affect the sign flag, or it'll affect the flags. So it could affect the sign, it could affect the 0, it could affect, affect the negatives. So we're going to say I want to put that in R0, and I'm going to test R1, which is our number, with our flags register, which is R0. And then this is something a little bit new. We're going to branch if equal. That means that the 0 flag was turned on to bit is not set. So branch if equal means that the 0 flag was not turned on, which means that those bits, that one bit, the 14th bit, we didn't have a 1 and a 1 to get a 1, so the result gave us nothing but 0. And if you look at these, this bit is turned on in the mask, and it's also turned on in our number we're testing. So this branch will not occur. So I'm just going to move into R0 on number 1 because the bit was turned on. If the 0 flag is not on, that means the result was greater than 0. So that's what's going to happen there. And I'm going to say bit is not set. That's a label. And I'm going to move into R0, the 0 value. So that's to check to see if a single bit is turned on. So let's make that. Let's debug it. Okay, so we're going to be looking for our MVN statement. There's our MVN statement. Now we're getting ready to check the 14th bit. So we do those things. We're going to AND S. So we're going to branch if equal. Now remember, those 2 bits were turned on. So branch if equal should take us to this line right here. So that means the 0 flag was turned on, which means the result was 0, which means those 2 bits were not on together. However, it doesn't branch to that, so that bit must have been turned on. Now this does take some practice, so I really would suggest that you try this out a number of times. Again, you can always go back and forth on this video until you figure it out. But that's how you test it out. So the equal is kind of weird. This will and our R1 with R0 and set any flags. That's what and S does. Okay? Branch equal, the 0 flag is on, so the bits were not on together. So branch. And this one right here, no branch occurred, so the 0 flag must be off, so the bits were on, or the bit was on, because we're just checking a single bit. All right, so that's checking to see if a single bit. What if I wanted to check to see if 2 bits are on? That's why I've got this value here. We've got the 14th bit and we've got the 3rd bit turned on in the mask. However, we don't have the 3rd bit turned on in our actual data. So that's going to be a little bit different, but I'm just going to copy and paste this. And so is the 14th and 3rd bits turned on. And we're going to do everything pretty much the same, except this time we don't need to use the and S, and you'll see why in just a moment. So we're going to and instead of 3, we're going to look at 4, because 4 is the bit mask that has the 2 bits turned on. So we're going to be looking at 1, and we're going to be looking at the D word binary 1 and 4. Now I'm kind of losing this in my scroll, and again, I keep these just to keep myself, what is it I'm comparing here? Okay. So we're going to and them together, and then instead of doing the BEQ, we're then going to compare the result that the and created and put into R0. We're going to compare that with R1. Now, why are we going to compare it with R1? Actually, I think we should probably have put that in. Yeah, I think I did something wrong here. So I put our bit mask into R2. So let's go over this code one more time. So I put the number we're testing into R1. I put the bit mask into R2. And then I'm going to put the result of the and into R0. So then what we're going to do is we're going to compare the result of the and with the bit mask to see if they're the same. If they are, that means both of those bits were turned on. So I'm going to change this to label to both bits set. And let's see how that works. Now, if you're a little bit confused right now, I don't blame you. What I would do is I would start this over again, try it with me. And this is a long video, but this is not a small concept. All right, so we're going to be looking for the first BEQ, and then we're going to move on to the next one. Okay, there's the BEQ. All right, so let's see what we got here. Okay, so here we are. Now we're at the code, which is right here, and let's go through it. So we're going to do the and. Now that's going to and this number with this number, and it's going to turn off all bits except for this one and this one. And if the result of that and is the same as the value of the bit mask, they're equal, that means those 2 bits were turned on. So I'm going to step. Now they aren't, because this bit, the 3rd bit here, is not on, but it's there, so they should not be equal. So branch if equal to this one down here, but it's not going to do that because they are not equal. So those 2 bits were turned on. and try to remember that we were at the move 1 right below the BEQ. And why do I want you to remember that? Is because I'm going to go ahead and turn this bit on now. Now I can't do it from a comment, so I have to go all the way up here and turn on the third bit. Start the debug again. Now I could have put a breakpoint here, but sometimes that takes a little bit longer. Okay, here we are. So now remember, on this branch, we went to this next line because that bit was not turned on. However, oh, wait a minute, it was the other way. So it actually jumped around that because that bit wasn't turned on. Now the bit was turned on, both of them are turned on, and it didn't branch because both bits were set. And I want to make absolutely sure about that. So let's turn that off again. Unless I didn't build it. I think I did, but this is assembler programming. Okay, here we go. Something's going wrong here. Well, let's get our bearings again. So, all right, so let's make sure we build this. All right, so this bit is turned on. This bit is turned on, so that one will be turned on after the end. That is off, and that is on, so that won't be on. So what we're going to do is let's debug it one more time. Good practice debugging. Okay, there's our first one. Go through that. And I think, I just want to make sure. Okay. Okay, so both of the bits are not set. So it did not jump to the both bits set, which is down here, this line of code right here. So now let's turn them both on and see what we get. Let's make sure we do the build. It's very possible I didn't do the build. Again, a breakpoint would be nice. All right. Now it should jump around that move R0, 1. We have a problem here. I don't know what the problem is. There's some bit that I'm messing up with. Let's make sure our code is right. So it could be the code. So I'm moving in R1. I'm moving R0 to R1. I'm moving the address of 4 into R0. I then move that R0 into R2. There's the error. I'm now ANDing R1 with R0, which is an address. I should have been ANDing it with the mask. That was the problem. So I didn't have my code quite right. So let's build it again. Now remember, both bits are turned on. So the third bit is on. The third bit is on. Now both bits are on, so it should jump around that, and it did. That time it worked. So it jumped around the move 1 to R0 because both bits were set. Let's turn off that bit again, and it shouldn't jump around it. Remember, it shouldn't jump around it. Okay, now it shouldn't jump around it. It should go to the next line of code, which it did. So that's how you can check. Whew, that's how you can check to see if multiple bits are on. So a lot of work, a lot of time. You got to get used to this stuff. It's like learning how to swim. It's like learning how to ride a bike. Try this stuff out. Start the video again. Do a little bit at a time. Understand it. Practice makes perfect. But that's how you can do it. I wish there was a better debugger. But right now, GDB is all we've got. And the next video will be another ARM video. This time, that video will be on array processing. So now that you know how to do the logical operators, now let's get into array processing. Hope to see you at the next video.